Hi, this is Zach Fulkerson, and this is the second part of acid-base in the critical care curriculum. In the first part, we went through some fundamentals of acid-base, and in this one, we're going to go through an algorithm for approaching acid-base problems. As a quick aside, the reason that we do this is that critical care patients often have serious acid-base derangements, and really being able to work through this can help you figure out what's going on with your patient. All right, let's get started. First, some conventions. Basic metabolic panel is shown here. Sodium, potassium, chloride, bicarbonate, BUN, creatinine, and glucose. You will see this tree a lot if you haven't already in your clinical rotations. Second, we have the arterial blood gas, which is going to be the pH, the arterial pH, the arterial PCO2, the arterial PO2. So this is what we're going to be using for acid-base problems. Real quick, some normal values. The pH is 7.35 to 7.45, PCO2 35 to 45, bicarbonate is 22 to 26, and the anion gap, this is a fairly broad range, usually around 12. I've drawn anywhere from 8 to 16, and remember that the anion gap is measured by taking the sodium minus the sum of bicarbonate and chloride. So let's get started with our algorithm. Step one is to check for internal consistency. This is using a modified Henderson-Hasselbalch equation. Step two is to decide if our patient is acidemic or alkalinic. This is fairly simple. If it's low, acidemic, high, alkalinic. Third is to figure out if this is the primary problem, metabolic or respiratory. Fourth is to check for compensation. So if you have a primary metabolic problem, you want to look to see if they have respiratory compensation and vice versa. Fifth is check the anion gap. Remember the formula for anion gap we just showed you. If it's elevated, you may consider checking for something called an osmolar gap. I'll give you the formula for that later on. And sixth, we're going to check if the anion gap is present. We are going to check for additional metabolic disorders. We only do step 6 if the anion gap is present, if it's elevated. First, internal consistency. There are two approaches to this. The first is the purist approach. This is what you learned in the second year of medical school, and that is to take that the expected hydrogen concentration equals 24 times the PCO2 divided by carbonate. This is a modified Henderson-Hasselbalch equation. So what you do is you take your PCO2 from your ABG, your bicarbonate from your BMP, and then that'll spit out an expected hydrogen ion. You go to one of these tables and you correlate your hydrogen ion concentration with what the pH is. These are really low concentrations, on the order of nanomolar, so they're very, very low. And of course, as the hydrogen concentration goes lower, the pH goes up. Now, a pragmatic approach would be just to look, if you happen to draw a blood gas at the same time as a BMP, you can really just compare the bicarbonate. It's shown as carbon dioxide here because this is total carbon dioxide, bicarbonate, carbonic acid, but it's mostly bicarbonate. It's shown here. You can compare that with your arterial blood gas bicarbonate. The reason is that this is calculated and this in the BMP is measured. So if they're close to each other, then you should have internal consistency. Places where we get inconsistent reading would be like if the blood gas is left out for a period of time before things are getting measured. When that happens, carbon dioxide leaches from the blood gas and it becomes more alkalotic. And so that's how we can get internal inconsistencies. So we have a purist approach and a pragmatic approach. All right, second step is acidemic or alkalinic. This is pretty easy. If it's less than 7.35, acidemia. Greater than 7.45, alkalemia. There we go. We've already figured out what our primary problem is if the primary problem is acidosis or alkalosis. Now, quick question. Does a normal pH rule out an acid-base disorder? Answer yes or no. So no, a normal pH does not rule out an acid-base disorder because, of course, you can have an acidosis and an alkalosis that are basically giving you a normal pH, but there can still be serious things going on in your patient. Next, primary disturbance. So basically, you look at the pH, which we've already done, to decide if it's acidosis or alkalosis. Of course, acidosis, the pH will always be low. Alkalosis, the pH will always be high. If you remember from, we're going to start with respiratory. If you remember from our first talk, a respiratory acidosis, the primary problem is that you're not blowing off CO2. So the CO2 is high and the pH is low. So if we've identified those two things, we have figured out that this is a respiratory acidosis. A respiratory alkalosis is just the opposite of an acidosis. Now on the metabolic side, the pH, of course, is the same. It's low if you have an acidosis. The only difference is that the primary problem is not CO2. In fact, we compensate by blowing off more CO2. So in terms of a metabolic acidosis, the PCO2 is high. So that is how you distinguish between metabolic acidosis and respiratory acidosis. It's really the PCO2. All right, so that is step 3. Step 4 is these equations that we all love to hate. And these are our compensation equations. So I'm not going to go into these in a lot of details. You will have them as a reference. One to really know by heart that you're going to see on board questions is probably this equation. This is Winter's equation right here, which is the expected CO2 equals 1.5 times the bicarbonate plus 8, give or take 2. Everything else I'm going to kind of let you look at on your own. So for instance, if you have an acute respiratory acidosis, you're going to compensate with bicarbonate. So for instance, for every 10 that the bicarbonate goes up, or that the CO2 goes up, the bicarbonate will go up by 1 if it's acute. And then for every then you kind of multiply that by 3.5 for if it's chronic. Anyways, I'm going to let you look through these equations yourself and really dig into them. We're going to get into them more when we do some actual problems. So these are your compensation formulas. Probably the most important one for you to remember is Winter's formula, which is shown right here. All right, this is compensation in other words. So for instance, metabolic acidosis, every increase in bicarbonate results in about a 2 increase in PCO2. Respiratory acidosis, we already talked about this. Every 10 PCO2 increases bicarbonate by 1 if it's acute, or 3.5 if it is chronic. Again, I'll let you look at these. I'll let you decide if you like more of the equation format of this or the verbiage of this. All right. Moving on to step 5. Step 5 is fairly simple. We measure the anion gap. And again, you do not need a full ABG to measure an anion gap. You can do this every morning in the ICU when you have a BMP. You take the sodium minus the sum of the chloride and bicarbonate. I'm going to consider 12, give or take a few, a normal range. If your albumin is low, which happens a lot in the ICU, you may have to add on to your anion gap. So for instance, let's say that you calculated the anion gap was 12, but the patient has an albumin of, let's say, 1.5. So that is 3 less than this normal 4.5. So we are going to add 3 times 2.5, which is 7.5 onto our anion gap. So our new anion gap would be 8. The reason we do this is because albumin is actually net negatively charged, and so it is actually one of our main unmeasured anions. So you have to correct for albumin if it's very, very low. Otherwise, you could really miss an anion gap acidosis. Look at this. We'll try to dig into it in terms of problems. All right, so step 5, again, if the anion gap is elevated, you may calculate an osmolar gap only really if you don't have an obvious cause. Like, for instance, if the lactase is elevated or you have a DKA, renal failure, whatever, you might skip this. But if you suspect that someone's ingested something like, ethylene glycol, some of the organic alcohols that people can become intoxicated on, you might calculate osmolar gap. Here's the formula. I'm not going to dig into this all that much, but it's 2 times the sodium minus glucose over 18 minus BUN over 2.8. Normal is about less than 10. Normal osmolar gap is less than 10. Finally, step 6. You only have to do step 6 if there is an elevated anion gap. And what we do this for is to figure out if there is another non-anion gap acidosis going on or a metabolic alkalosis going on. So we take the change in the anion gap, so how much the anion gap differs from normal, so I use 12 as my normal, divided by the change in bicarbonate. This is why this is called the delta ratio or the delta-delta ratio. All right, so like for instance, if the anion gap is 24 and my serum bicarbonate is 12, then I would have 24 minus 12, that's 12, and 24 minus 12 is 12 here. So I would have 12 over 12, and that would be 1. If this ratio is 1 to 2, that means that you really only have an anion gap metabolic acidosis. If the ratio is less than 1, that means that our bicarbonate is really a lot lower than we would expect for just an anion gap acidosis. So that means we have a non-gap acidosis as well. Remember, a low bicarbonate suggests an acidosis. So if the bicarbonate is lower than we would expect, i.e. this ratio is less than 1, then we have a metabolic elevated gap acidosis as well as a non-gap acidosis. If the ratio is greater than 2, then that tells us that the bicarbonate has not decreased as much as we would expect. And what metabolic processes result in a high bicarbonate? It's a metabolic alkalosis. So again, less than 1, you have 2 metabolic processes, both a gap and a non-gap acidosis. Greater than 2, you have 2 processes, a gap acidosis and a metabolic alkalosis. So that does it for acid-base 2. Next, we're going to go through a multiple acid-base problem with you to show you how to do this yourself.